Next speaker is Tim Pelsma. Yeah, come on up. Yeah, take some water. And Tim is from the Netherlands. He will present a social cost-benefit analysis of peat soil subsidence towards 2100 in 4 scenarios.
Thank you, Saskia. Hello, everybody. I hope you're still awake and fresh. My name is Tim Pelsma, and I'm going to tell you something about a social cost and benefit analysis, shortly SCBA, of soil subsidence in peaty areas, grassland areas, towards 2100 in 4 scenarios. I did this together. I wrote a paper that you can download in the website, and it's also in the thick book, I think, but under the same name, together with Anna-Marika Motelica, also present in the audience today, and Simon Troost. Anna-Marika and me work for the Water Authority, was mentioned before today. The Water Authority is Amstel, Gooi en Vecht, is in the Amsterdam area. And Simon Troost is from Het Zaland Counseling. He did most of the basic work. I'll come to that later. This is our Water Authority area. In the top, in the yellow, is the city of Amsterdam. And basically the area where we work for in the peat area is between the cities of Amsterdam and Utrecht. It's shown here. We have an executive agency which is called WaterNet. We work as WaterNet for the Water Authority and for the city of Amsterdam. As Water Authority, one of our main tasks is to manage the levels of the ditches in the peat areas and also all kind of other waterworks. But for this presentation, the ditch levels in the peat area are the most important. And it is about 20,000 hectares of drained peatland for only this Water Authority. At present, the ditch levels are about 30 till 60 centimeters below surface, which results in a groundwater level of between mean annual 30 until 80 centimeters below surface. In the study area, we experienced a soil subsidence of roughly 9 millimeters per year, or a little bit less. And that is mostly because of oxidation of the peat, because it's drained peatland. This is how it looks like if you go on the bike between Amsterdam and Utrecht. Just a random place, well, grassland, of course, with farms and cows and a lot of ditches. And was doing some research here to the soil. This is the same area between Amsterdam and Utrecht, and in purple is the presence of peat. The darker the purple color, the thicker the peat layer. And the gray areas are the urban areas or water, or at least there's no peat there, clay area, sand. The top of the map is the city of Amsterdam, is of course all covered with buildings and roads and city. Why did we make this social cost and benefit analysis, shortly SCBA? That is because we think the current policy could change soon. And the current policy is to lower the ditch levels every 10 years. So we follow the subsidence, basically, causing the subsidence to stay there. But we also aim to contribute to a sustainable land use of peat areas. This is a new development for the recent 10 years or so, or even last 5 years. And we considered in this CBA several things. But first, water management costs. It's about costs and benefits, of course. Houses, foundations, also a cost. Infrastructure and farmland as well. That is a benefit because dairy farming, you can profit from that. But also in the farms themselves, they experience also costs because of soil subsidence. For instance, because of wet spots in the meadows. And last but not least, the peatlands and ditches, they are a big source of greenhouse gases. We estimate about 5% of all national emissions, not in the EGV area, but all peatlands in the Netherlands. And if you take this into account in an analysis, at the price of 40 euros we used. This was 5 years ago, but nowadays it would already be 97 euros if you look to the ETS European system for carbon pricing. And as I said, peatlands are also fertile meadow soils, so it's good farming there. And that's one of the benefits. And as you will see later, if you're going to change the system, the benefits of the farms will change too. Material methods, how did we do this? And the base assumptions in this study. First of all, we started in 2017 and then we made calculations for 2027, 2050, and finally for 2100, meaning short term, one period of policy, 10 years or so, and then 1 generations, and then at last 2 generations, or even 3. We studied 4 scenarios. Present policy, that is lowering the ditch level every so many years, like the picture I showed you before. On the right you can see some impressions of how this policy would look like, this scenario. Active re-wetting is the second scenario. This is a dramatically wetting scenario in which the level of the ditches is raised almost to the land level, just 10 centimeters below. Well, as you can see, you get a lot of water on the land then, so farming will be hard, but CO2 emissions will probably drop to 0. Methane not, but that's something else. Passive re-wetting. Passive re-wetting is doing nothing basically and wait until the subsidence goes to the water table, to the ditch table and the groundwater table. And we calculated that it could cost up to 80 years to be very wet. So passive re-wetting means you have a good result towards 2100, but you will have to wait a long time. And the last scenario is submerged infiltration drains, as shown here a little bit. Then you put these infiltration drains every 6 meters in the meadow, and that is under the surface of the ditch level, so the water can infiltrate in the summertime and will drain in the wintertime when it's raining. We used a tool for this. It was mentioned before in the presentation of Henk van Hardeveld. This is the tool called Repeat. It was developed by our neighboring water authority in the Utrecht surrounding. And it includes the Phoenix subsidies formula and other features as well. I have to leave that out in this short time. Well, what did we look at further? To stakeholder teams and kind of effects, we considered the water authority itself. So we managed the dikes and the sluices and etc. Cost for that, sludge removal too, cost for dike and maintenance and shortage of water storage that I have to explain. If you raise the level of the ditch and a rain shower comes, you have less space for water to put away, so you'll get troubles with wet areas. Public works, households, nature and landscape, farms and food supply chain, and environment as in greenhouse gases mostly. Well, then we put all these things in the computer program and then something comes out. And these are the results in millions of euros. It's hard to read, so I pick a few highlights out. At present policy, that's the left column here, we can compare with active re-wetting, the most dramatically scenario. And you will see 2 things. You see a sharply decrease of farming income. It will drop from 7 million euros to 2.5 million euros, which probably means farms cannot stay there anymore. And also, on the other hand, the greenhouse gases will drop from 18,000 euros at a cost price of 40 euros a ton, so it would be different nowadays, with something like 3 million euros to 15 million euros. So active re-wetting means the farming profit drops sharply, but it has the strongest effect on the reduction of greenhouse gases. But there will be a considerably large number of amount of CO2 still be emitted. And passive rewetting, it gives the strongest cut in costs for the water authority, as you can see on the third column for the water authority. There's the pointer here. It will go from 37 million to 29 million euros. And for the houses, there's a difference too. And the infiltration drains, where is it? There it is. For the infiltration drains, there is something remarkable. We see almost no effect on the considered features in this study. But there's a reason for this. We assumed that the mean water table doesn't change when you put in infiltration drains. It will raise the groundwater level in the summer times, but it will drop the groundwater level in the rainy winter times. Perhaps this is not a right assumption, but this is what we did in this study. And if you look to the subsidence itself, what changes do we see then? After 84 years, so that is in the year 2100, we still see, even with active rewetting, some remaining subsidence between 10 and 50 centimeters. And this is also the reason we still see CO2 emission. If we go to passive rewetting, in the end it's just as wet, but it will take a long time to get there. So it works slower, 15 to 75 centimeters of remaining subsidence in the same time. And for infiltration drains, it's a wide range. We see between 15 and 100 centimeter remaining subsidence in the same time. This is an interesting picture. This is a difference picture. So we compared the three scenarios with the present time with the base scenario. So you look to the differences in outcome here. The top part is the submerged infiltration drains. Will give a little bit less costs overall, but not a very, it's almost the same as present policy. So you could also say infiltration drains mean you can go on like we go now for farming, and the costs and benefits will remain more or less the same. That is included the costs for the infiltration themselves, but there is not much reduction in greenhouse gas emission. On the contrary, if you look to the passive rewetting in the middle here, you see a big, in the first decade or so, not much happens, but then the subsidence goes on and it becomes wetter and wetter and wetter, and then big changes are being visible. It costs 15 million euros a year, and it's mostly caused because of the cost for the water authority. So it was kind of a surprise for us. So that doesn't mean we have not much work for every 10 or 20 years or so for new dikes, new sluices, new pumps, etc. And then we finally look to the active rewetting, and then you see this right part, which is in the benefit area, and that's loss of benefit actually for the farmers. Logically, if you active rewet your area, it's not suitable for farming at once, you could say. Thank you. I'll speed up a little bit. We also look to the sensitivity for input. Of course, it's very sensitive for input, as it is with every model. But especially for milk price and food price, the interest, so the financial market, you could say, has a strong effect. But also climate scenario. We use the strongest climate scenario in the calculations as I showed you. But you could also choose a less extreme climate scenario. You see a big change. Conclusions and discussions. An CBA is not an exact science. It gives a clue. It gives direction for policymakers on the long term. Change of current water management is necessary to reduce social costs and greenhouse gas emissions and costs from that. The highest short-term impact will be reached by active rewetting. but also the strongest effect on farming. However, polyculture as an alternative for farming was not included in the study, so that could change things. And on the long term, passive rewetting has the best outcome, you could say, leads to the strongest cost reduction. And to improve future SCBA's, we need better data, of course, especially groundwater data and data from the greenhouse gas emissions itself, but they are available in the meantime. So this is my colleague doing good work here against soil subsidence that is measuring. Any questions? Thank you.
Thank you, Tim. I can imagine there are some questions.
Yes, thank you for this nice and interesting talk. Maybe a little bit a technical question, but you, one of your conclusions was that the subsidence after active rewetting, subsidence remains 10 to 50 centimeters in 84 years' time. I was wondering why, because the oxidation will stop. Is this ongoing compaction or creep?
Altogether, it's ongoing compaction, but it's also a little bit ongoing oxidation. Because in the summer times, in warm and sunny conditions, the water table still drops if you don't take extra measures. And I didn't tell, but in all the scenarios, you still follow the soil subsidence, what we call indexation. So we don't stop indexating. We just stop the soil to go down. But if it goes down, we follow
yes.
with the ditch level 2, except for the emerged infiltration drains.
Okay. Thank you.
And except after active rewetting. Thank you.
Okay. Other questions? Yes.
Thank you for your presentation. I have a question. What is the difference between a rising groundwater level and rewetting?
No, that's a good question. Thank you. It's when you rise the ditch levels, you rewet the area, and if you do that very well, so it's a high rise, then the rain which falls in the wintertime cannot go anywhere. So it can only go up, and that will raise the groundwater table too, but just in rainy winter times. Does this answer your question or not?
No. Do you apply groundwater leveling up or down, in this case up, or do you in another way rewet the land?
In a scenario of active rewetting, we just use the ditch level as an instrument. And it has some advantages and disadvantages, of course. If there is downwards leakage, and sometimes there is downwards leakage, you cannot raise the groundwater level in the middle of the field, just in the sides of the field near to the ditch.
Yes, but your regulation system is mainly variation of groundwater level.
That's right.
Thank you.
Okay. There's room for one more question. I have one for you, Tim. Looking at all these interesting results, what are you proud of? Can you mention that word from your personal experience?
That's a good question. That the study has been done anyway, I'm proud of, because we started in 2016 or 2017 to ask questions from to the market, because this is complicated work to do. So that's why we asked Simon to help us. And we looked for money for doing the work, which was also not very easy. And I'm proud that it worked out altogether to this result. So as a whole.
Yeah. Okay. Can imagine. And still a lot of to be done, to be continued.
That's
Thank you.
True.
Thank you.
You're welcome.
Well, stand up, please. Then we get re-energized and we give Tim And our next speaker, Michael, a big, big, big applause.